Last week, we took a quick look at what I call the eigenvalue question. The eigenvalue question. In some books, you say it as the eigenvalue problem. There is a particular funny behavior of tensors. And that is a situation where the tensor does not seem to be obeying its own rules. It is breaking its own laws. For instance, we know that if you have a tensor and you give it a vector, that vector will be transformed. It will be rotated and it will be elongated or decreased in length. So those two things will happen. How much rotation and how much elongation, you don't know. You can only know by calculating. You have to calculate it. But we said there are certain cases where there is no rotation at all. All that can happen to that, all that will happen to that vector that is being transformed is that it becomes longer or shorter, which is as if you have just multiplied it by scalar. A whole tensor is pretending to be a scalar. All that happens to that vector is that it is as if it has been multiplied by a scalar. Now, and the funny thing is that it does not do that to every vector. It only does that to a few vectors, but it would now behave normally with every other vector. So why is that behavior? It turns out that a study of that behavior is one of the most important mathematics you will ever learn. As an engineer, that behavior of that tensor, where it does not transform all vectors in the way that you expect, where it just transforms some in a very funny way, which is just elongation. That behavior is so deep and is so important to every engineering discipline. If you are looking at electricity, if you have an LRC circuit, an inductor, a capacitor, and a resistance circuit, those are oscillations in that circuit. Those values of that tensor will give you the oscillations of that circuit. If you are a civil engineer and you are looking, or mechanical engineer, and you are looking at stresses, those will give you your principal planes and your principal directions. If you're a mechanical engineer and you are looking at mechanical vibrations, those are going to give you your mode shapes, as well as your resonance and all the frequencies that you have to avoid. That particular mathematics came from an engineering problem. And so mathematicians have gone a long distance in actually giving far more information about what happens when we have the eigenvalue issue. The eigenvalue or eigenvectors, as you will come to know them, is so critical that I have decided to expand my notes. I've done some little more work to explain it deeper, more deeply to you. My intention today is to first of all make you see that the issue of the eigenvalue is a very simple concept. So simple, and we will first of all distill that concept before we start working mathematics. The main problem you have is that you rush to the mathematics without understanding the concept. You will discover that if you understand the concept, the mathematics is not as hard as it appears. The mathematics is just merely some working out, and you will see that what are you doing? You are either doing matrix multiplication or gathering terms, or those things are not the issue. The issue is, do you understand the concept? So the first 10 slides will attempt to that eigenvalue question arises in tensors. It also arises in matrices in exactly the same way. Therefore, you are often able to use your matrix knowledge to solve a lot of tensor equations. And it is important to see what the difference then is. Because of that, people think tensors are matrices. So I will continue to emphasize to you that a tensor is not a matrix, but all tensors have some matrix representation. But that is not all there is to them. For instance, a vector can be represented by a matrix. You can say 1, 2, 3 is a vector. But that is just its matrix representation. What you really mean is 1i plus 2j plus 3k, because those 1, 2, and 3 are just the projections on the 3 different coordinates. They are not numbers that are just arbitrary numbers doing their own thing. They have specific geometrical meanings. So, whereas a matrix is an algebraic concept, a tensor is a geometric concept. And in many cases, because tensors always have matrix or algebraic representation, there are a lot of computations you can do with that. But it does not therefore mean that a tensor is a matrix. And I cannot overemphasize that. But let us go back to the issue of the eigenvalue question. I want to develop it, and I will show you some, I will do some computations. We will do some computations together to reinforce the idea. So my first task is to explain to you what the eigenvalue and eigenvectors, what they really are. So once you know what they are, the rest of the lecture today will now do some mathematics. But please pay the biggest attention to understanding the concept and ask me questions if there is any aspect of the concept that is not very clear to you. I will not be angry. I will be patient, because there is nobody in this class that cannot fully understand what eigenvalues and eigenvectors are. I know you meet this in other courses and it look like magic, but there's no magic there. It's a very, very, very simple concept. So let's move on. Last week, I tried to explain to you that there are certain similarities between vectors and tensors. For instance, you can represent vectors in terms of 3 coordinate bases. Similarly, you can represent tensors in terms of 9 dyad bases, which are combinations of those same coordinate bases. There's somebody is saying something here. So you can see that we can also write vectors in component form like this: V1i, V2j, V3k. Similarly, we can write tensors in component form, and there will be 9 components to the 3 of the vectors. We can evaluate each component by taking scalar product, and we can do the same thing in the tensor by taking scalar product. We defined the scalar product of tensors either last week or week before the last. So if you take the scalar product, just like the way you do with vectors, you are going to get the components. You are going to get 9 things because there will be 9 combinations of the dyad that you can take the scalar product with, and it will give you those 9 components. Similarly, scalars have magnitude, tensors also have magnitude. There are scalar products. It's just that more than one scalar product is defined for the tensor, but we are only dealing in this course. We are only dealing with the first one. We will ignore the second one for now. There are many products you can define for tensors, and what is most useful for us at the beginning is what I am going to deal with. Then, because scalar products can be obtained and they are scalars, when the scalar products equals 0, we say those 2 vectors are orthogonal. The same thing, when the scalar product between 2 tensors are 0, you say those 2 tensors are also orthogonal. The only thing is that whereas you can do a geometrical drawing for the 2 scalars, then for the 2 vectors, in the case of vector, you do not have that same benefit when it comes to tensors. You cannot really draw and get an angle 90 between the 2 tensors, but algebraically, they are also orthogonal. Then we said there is a 0 element for vectors, which is the 0 vector 0i plus 0j plus 0k, or 0e1 plus 0e2 plus 0e3. Then the same thing, there is a 0 tensor, which is the annihilator tensor, which is 0e1 circle times e1 plus 0e1 circle times e2 plus 0e1 circle times e3 plus 0e2 circle times e1 plus 0e2 circle times e2 plus 0e2 circle times e3 plus 0e3 circle times e1 plus 0e3 circle times e2 plus 0e3 circle times e3. So those are the 9 components. Don't be lazy and don't rush. The thing actually has meaning, but you can actually represent it in its matrix form. But the matrix form is not the tensor. The tensor itself is when you include all the directions of the dyad that the numbers represent. There is a matrix form, which is part of the tensor, but it's not all of the tensor. So people who say tensors are matrices are partially correct. There are, but they are partially correct to the second order. By the time you get to third order tensors, there is nothing like matrices. These things are now multidimensional, and the matrix is no longer applicable. So when you say that a tensor is a matrix, you are limiting yourself to second order. And even in zero, first and second order, you are not completely correct. But when you get to higher order, there is just nothing like that at all. So better know that if you understand, anybody who says a tensor is a matrix does not know tensors. It does not know beyond second order. But we are going to go to third order. We are going to get to the fourth order in this course. So let's be very clear on that. But every tensor has some form of matrix representation. But that matrix representation does not tell you everything. And then we also talk of products, and we explain that there are several kinds of products when you are dealing with, for instance, when you are dealing with vectors, you only have 4. The multiplication by scalar, the scalar product, the vector product, and the tensor product. The tensor product can generate a tensor from any two vectors. When you come to tensors, the number of products multiply exponentially, but we are again only limiting ourselves to some few products for this course. We don't need to, we pretend as if those other products don't exist. We don't need to worry about them now. So the eigenvalue question. We received formulas for computing principal invariance and took these formulas as definitions of the principal invariance. These formulas arise from deeper analysis, very deep analysis. We already saw that the cofactor transform area. We showed that the determinant relates transform volume to the original volume. We will ask this question from the standpoint of tensors and show how it leads us to several important results that greatly assist the engineer in the solutions that may not have been possible otherwise. Let me just correct the grammar in that place. The results assist. Okay, so for instance, if you have 3 sides of a parallelepiped with vectors u, v, and w, as shown in the top picture here, suppose you transform each side with a tensor t. That will give you vectors tu, tv, and tw, because if the transformed vector, the transformed vector is still a vector, and it too can form a parallelepiped. The question is, what is the relationship between the volume of the transformed parallelepiped to the original parallelepiped? The answer is that the ratio, the volume ratio, is the determinant of the tensor. That determinant can be computed. Just divide the original, the final transformed volume by the original. The number you get is the determinant of that tensor. So because we are dealing with geometry here, the things we are talking about, they have geometrical interpretation. Similarly, if you have an area that was bounded by vectors u and v, and you transform to tu and tv, and you want to know what is the relationship between that original area and the final area, the answer is the cofactor. The cofactor, because the area of the first one is a vector, the area of the second one is a vector. It is a cofactor transformation that transforms the areas. Whereas the original tensor transforms the lengths, the cofactor transforms the areas. We talked about that last time. So all these things we are talking about, the determinant and the cofactor, they have geometric interpretations. And if you stay with the geometric interpretation, you can also go back to the algebraic interpretation, the algebraic interpretations of matrices. You are going to get the same thing. But notice that when we are dealing with tensors, we are much more interested in the geometry. So the question again, the eigenvalue question, a tensor linearly transforms one vector to another. We cannot always predict the outcome of a tensor transformation other than the fact that we know that what comes out must be a vector and that the transformation is linear, in the sense that if you transform 2 vectors and somebody transforms the addition of the 2 vectors, the addition of the transformed vectors will be what he will get. So that is the linearity there. If we know that, if we know that the transforming vector is a special tensor, such as an identity, for instance, if you know it's an identity, you transform, you know nothing will happen to the vector. Input is equal to output. If you know it's a spherical tensor, you know that that vector will be multiplied by a scalar. If you know it's an annihilator tensor, you know that that tensor will be completely reduced to 0. If you know that it's a rotation, you know that all that will happen is that the vector is rotated and there will be no change in its magnitude. So we may have additional information that helps us predict what the outcome may look like. If you don't have that additional information, then we have to do computation to see what the final result is. The eigenvalue problem. We pose this question. Suppose we have, for a particular tensor that we didn't know it to be identity, we didn't know it to be spherical, we didn't know it to be a rotation, we didn't know it to be an annihilator. We just know that this is just an arbitrary vector from nowhere. We were given that vector, we were given that tensor. Suppose we have that. When we use it to transform the vector u, the answer we get was still in the same direction as u was. It's just that it has multiplied u by a scalar. And that it does this not to all vectors, but to some specific vectors. If that is how that behaves, what is happening here? What is the problem? Why is it behaving like this? Because ordinarily it's supposed to change the magnitude and rotate the vector. But this particular one, it refuses to rotate. It only elongates or contracts. Remember that a rotation tensor does not change length, but it just rotates. This particular one does not rotate at all, but changes length. And it doesn't do, but for a rotation tensor is a simple thing because it will rotate every tensor the same way. If it is rotating it to a particular degree, everything you give it, it will rotate it to that particular degree. So a rotation tensor does not give us the problem that we are getting from the eigenvalue problem. A rotation tensor is consistent. If it's rotating, it is rotating. And it rotates by the same amount, no matter what you give it. If it is 30 degrees rotation, anything you give it will be rotated by 30 degrees. And that's all it will do. But the eigenvalue problem arises because this tensor does not rotate, but only elongates or contracts, and does not do that consistently for everything. So if you can give it one vector, it will behave normally. But you give it another vector, it behaves abnormally. So you are wondering what is happening. Now, when you have that situation, you have what is called the eigenvalue problem. And that is what we want to understand a little bit of in today's lecture, the eigenvalue problem. The question, note what is happening here. The tensor is pretending to be a scalar, or at least a spherical tensor. Several questions arise. Why does this happen? If it is neither, if it is not a scalar, why is it behaving like a scalar? If it is not a spherical tensor, if it's a fully populated tensor with, in fact, with non-zeros everywhere, why is it behaving as if it was a spherical tensor? Is there any relationship between the tensor and the vector that produces this special location? Is there? Because it doesn't do this for all vectors. It does it for some specific. Let us say we are able to gather those specific vectors that it does it for. Is there anything that connects them to this particular tensor? What about the scalar multiplier? What happens if the scalar multiplier is unity? And when the scalar multiplier is unity, that means it is behaving as if it is an identity tensor. If the scalar multiplier is unity, then the tensor is behaving as if it's an identity tensor because it does nothing. So, eigenvalue, a characteristic value. So we will discover that the eigenvalue is a characteristic of the tensor. And the eigenvector, they are specially related and tied to the tensor. So you can actually go and find them. And we are going to develop the equations we will solve that will yield their values to us in this class. The vectors that satisfy this equation we have been looking at are called eigenvectors. And their corresponding scalars are called eigenvalues. That word eigen is German. It's a German word. The correct English word is characteristic. The word eigen is characteristic. So you will see some textbooks that say they call the eigenvectors characteristic vectors and the eigenvalues characteristic values, because those values are characteristics of the tensor. So they are belonging to that tensor, knows those values, and usually in a three-dimensional space, there are three vectors that will satisfy the characteristic equation, and there are three scalars. So there, in a normal situation, you have three eigenvectors and three eigenvalues. But we will even get to some abnormal situations later on. But normally, there will be three vectors and there will be three corresponding eigenvalues. That is normally. But it is not, things are not always normal. So once you know the eigenvalues of a tensor, you already know the principal invariance in a form much simpler than the equations we saw last week and the week before. In fact, you know everything you want to know about the tensor. So often an engineer does not care. Once he knows the eigenvalues and the eigenvectors of a tensor, he doesn't worry about anything. There's nothing you want to know about that tensor that you don't already know. And so many times, whenever we have a tensor, we are just looking for the eigenvalues and the eigenvectors because nothing else matters. You will think that you need 9 components to define a tensor. No. If you know the eigenvalues, if you know those 3 eigenvalues, you can calculate all those 9 components from them very easily. So there is no problem at all. The eigenvalues and eigenvectors are often the quantities engineers seek for in a typical tensor. Its physical interpretation is wide and diverse. For material science, where the eigenvalues represent principal stresses, while eigenvectors represent principal surfaces, to dynamics where they are natural frequencies and mode shapes, and to electric circuits and several other applications. They spread through everything that causes engineering has an eigenvalue problem. Okay, now let us make it very easy. Begin with a vector. Let's just take a very simple vector. V1 is equal to E1 minus E2 minus E3, or if you are used to IJK, it is I minus J minus K. That's a simple vector. So we want to transform it with a tensor T, where the tensor T, I have expressed tensor T in its full dress. I've gotten the 9 components in the 9 dyad pairs. 3E1, E1, plus 4E1, E2, minus 2E1, E3, plus E2, E1, plus 4E2, E2, minus E2, E3, plus 2E3, E1, plus 6E3, E2, and minus 3E3, E3. So that is the tensor in its full form. We can write that same tensor in this more compact form, which is exactly the equivalent. If you carry out this circular product here, so it is just the ordinary product. So this is a 1 by 3, this is a 3 by 3, and this is a 3 by 1. What we are saying here is that whenever you are taking a product of this, you put a circle times inside between the beginning and the one on the left and the one on the right. That's all. Otherwise, we can just remove this and just take it as if you have 3 matrices multiplying each other, and it will just be the same result. It's just that for all your E1 and E2, they will not just occur together. There will be a circle times in between them, and you will get this one. Work this out, you'll see. If you work out this transformation, if you work out this, you will get that TV1 is E1 minus 2E2 minus 3E3. And this is where problems start. You will nod your head like a lizard. And maybe some of you will not know how we got from here to here. How did we get that this is what is there? How? And some people will cram that, and they will be the brilliant students, even though they don't know it. And when the teacher asks, they give him back what he gave them. Some people, some better students are in class, they will fail because they are struggling and struggling and struggling. How did the man get this? How did it happen? Okay, so I want to neutralize that doubt and go straight to see how I got it. But let us see. You can see that when you operate T with V1, you see, let us look at E1 alone. When E1 is multiplying this, you will get 3. When it is multiplying this, you get 0, because you will see that there will be a dot product between E2 and E1. When it does this, it gets 0. So it only produces value when the thing on the right-hand side is E1. It produces nothing when the thing on the right-hand side is any other thing because of the orthogonality. Similarly, when minus E2 is multiplying this, you get 0. When minus E2 is multiplying this, you get -4. When minus E2 is multiplying this, you get 0. When minus E2 is multiplying this, you get 0. When minus E2 is multiplying this, you again come back and get 4. When it is multiplying this, you get 0. When it's multiplying this, you get 0. When it's multiplying this, you are going to get -6. When it's multiplying this, so just know that that is what happens. So we can then do the product bearing that in mind. If we do the product bearing that in mind, you will get this kind of arrangement here. It's only when E1 is on the left-hand side that you're going to get E1. So, and the only one that will produce non-zero are the ones that here, the only one that will produce non-zero. Oh, sorry, there's a missing, I have a missing bracket there. Let me just put that bracket so that it doesn't constitute a problem. And then I continue with my slideshow. Okay, so like here, if you want to now know the things that give a coordinate for E1, it is this one, and this one. But this one, there will be no product for E2, there will be no product for E3. This one, there will be no product of E1, no product for E. So if we do it, all that will come out of E1 is 1. Why? Because this one will give us 3, this one will give us -4, and this one will give us +2. So if you have 3 -4 +2, you are going to get, if you have 3 -4 +2, that is 5 -4, that gives you 1. Similarly here, you have 1 -4 +1. So that gives you -2. Here you have 2 -6 +1 gives you -3. So that the transformation TV1 is equal to E1 -2 E2 -3 E3. That is how we obtain this. If you do this thing graphically, let us say we have our axis, Z-axis pointing up, Y-axis pointing right, and Z-axis pointing towards us, this blue axis. If you write the input vector, the input vector is 1 -1 -1 in the 3 axes. So if you first of all move 1 along x-axis, and then you go -1, -2 on y-axis, and then you go -3 on z-axis. Oh, sorry, I'm talking of if you have 1 on the x-axis, you have -1 on y-axis, and you have -1 on z-axis. You have this blue, you have this green. The blue line there is x-axis. The green one is the input vector V1. Similarly, the output vector is 1 -2 -3, and that gives us the red. So when we do the transformation, you can see that the original vector has been rotated and has been elongated to get the final result. So that is the normal thing that happens. That's normal. So we can also go ahead. We could have used the matrices. We could have used the matrices to evaluate this. This is the matrix of the tensor. This is the matrix of the input vector. And if you do this product, you have -1 -2 -3. Of course, it is obvious that this is an easier and neater thing to do. So we like to work this way because this gives us the answer very easily, and we can even program this. We can use mathematical or something. But the fact that our matrices help us to get the answer quickly does not therefore mean that the tensor is the matrix. That's what I'm trying to emphasize. Just note that. So that shows that because this is the matrix of the tensor, and this is the matrix of the vector, and this is the matrix of the resulting vector, and there is no problem as long as you know what you are doing. No problem. Use it to get your answers quickly instead of going through this complicated, instead of going to, because you are going to get the same answer whether you use the tensor geometry or you use the matrix algebra. But the matrix algebra gives you an easier way to get to the answer. So use it. And so, but using it, don't therefore conclude that you are now that vectors and tensors and matrices are the same, because you can see that this tensor has a matrix, but has more than a matrix. That's other things. And similarly, this vector can be written in the matrix form, but you can see that the full form is when you notice that those numbers are the projections on the directions. Those are the important things for you to be aware of. So that is the tensor. The tensor operates on a vector, rotates and elongates it. That is what you have. You are supposed to have a rotation and an elongation because vectors have magnitude and direction. When you have a new vector, the new vector will show it's a new vector by having its own direction, which may not necessarily be the same as the original one, and having its own magnitude, which may be different. That is how you know that you transform one vector, you get another vector. So that is a normal tensor operation. So this is the same tensor operation, but we work out the numbers using our knowledge of matrices. Now, we could also use Mathematica. If you want to use Mathematica, you can write out the matrix form of the tensor like this. M is 3, 4, minus 2, 1, 4, minus 1, 2, 6, minus 1. And then you can even ask it to give you the eigenvectors of the matrix where it gives you the matrix form of the eigenvectors. You can define V1 as 1 minus 1 minus 1. That is the thing. And then you can now ask for M dot V1. It gives you 1 minus 2 minus 3, which is what we were expecting. So, but here we defined other vectors. We defined another vector 1, 2, 1, 1, 2. If you do M times V2, what you get here is 3, 3, 6. You can see that 1, 1, 2 and 3, 3, 6 are the same vector, only multiplied by 3. Now, why is that so? It is so because 1, 1, 2 is one of the eigenvectors of the matrix. So that is why that happens. If you do it for 0, 1, 2, because 0, 1, 2 is also one of the eigenvalues, eigenvectors. 0, 1, 2 will give you 0, 2, 4, which is just, if you do it again for 1, 0, 1, in the case of 1, 0, 1, it gives you back 1, 0, 1. That means that for 1, 0, 1, 1, 0, 1 is not just the eigenvalue of this tensor, it is actually having an eigenvector of 1. So for this particular last one, it is behaving not just as a spherical tensor, it's behaving as an identity tensor. That's if you've done nothing to it. So we can show this result. One of them, I decided to pick the second one. That is the second one as the one with V3 as an example. And I did it. So for V3, which is 0, but what is it now? Okay. 0, 1, 2. That is E2 is 1, E3 is 2, and E1 is 0. 0, 1, 2. So you go 0 along the x-axis, so everything is on the ZY plane. So when it's on the ZY plane, you move 1 unit on the Y plane, on the Y-axis, and 2 units on the Z-axis to get the one that is drawn with the grain here. It's difficult to see it because the other one overshadows it. So when you now do the product, like when you do the product, you have 0, 2, 4. So everything is doubled. So you go 2 units on the Y-axis and you go 4 units on the Z-axis and still 0 units on the. So this is what happens. This is what happens when a tensor is operating on its eigenvector. The answer is still along the same eigenvector multiplied by the eigenvalue that corresponds. It means that the corresponding eigenvalue in this particular case 2. The eigenvalue is 2, and the eigenvector is 0, 1, 2. So that is that's how an eigenvector is transformed. So you can see that the idea is simple. There are certain vectors associated with the tensor where when you transform, it won't behave in the general way. It will still change its magnitude, but it's not going to change its direction. When there is a vector like that, that vector is called the eigenvector of that tensor. And the scalar multiple of that transformation, which is a scalar number which can be less than 1 or bigger than 1, it can be positive, it can be negative, and that is what you call the eigenvalue of that that is corresponding to that eigenvector. So everything is in pairs. For every eigenvalue, there's a specific eigenvector. And for every eigenvector, there's a specific eigenvalue in the general case. Later on, we're going to get to specific cases where things are a little bit more difficult than that. But that is the theory, that's the background to the issue of eigenvalues, eigenvectors, because there are certain vectors that when you operate on them, you do not get the general result of change of angle and change of magnitude. You just get change of magnitude only. Nothing else happens. When that happens, we say that if it's happening to a full-fledged tensor that is not a spherical tensor, then you say that particular vector is simply an eigen vector of the tensor, and the value of its multiplication is the eigenvalue. I think we have. I want you to digest that. I want to stop there. I will continue after. You will come back from your break at noon. I give you 19 minutes break. You come back at noon. Just please take a look at what we've discussed, and then we will now move on to other issues from this point. Thank you.